Hello everyone, in this video we will be looking through the problem which is really connected to the material balance stuff, and we'll be looking through the problem which is with the three tanks that are interacting with each other. So here we have our question. So three tanks with cross-sectional areas of 0.5, 1 and 2 meters square are interconnected at their bottoms with initial fluid height levels of 0.5, 1 and 2 meters respectively. The magnitude of the flow between the tanks is proportional to the square root of the difference in fluid height between pairs of tanks. The proportionality constant between tanks 1 and 2 and tanks 2 and 3 are 0.1 respectively. Tank 3 drains to the surrounding at height of 0 with the same proportionality constant. Using the simplest form of control for the fluid level in the third tank, proportional control, the flow into the second tank is set equal to the proportionality constant, which is 0.1 multiplied by the difference between the fluid level set point for the third tank, 4 meters, and its actual fluid level. So here in the first, we're given some values, and in the first part of the question we're asked to derive the differential equations to solve the fluid levels in the three tanks. So here we have our diagram to represent what is happening in our problem. So we have three tanks that are connected with each other. So there is they have different heights and their own cross-sectional areas, and there's a flow between three tanks. So it can either be it can be going each way. So the flow of our fluid is kind of related to the height of our tanks. So if the height of tank 1 is greater than the height of tank 2, the fluid is going to be moving from tank 1 to tank 2. But if it's vice versa, we're going to experience the fluid in the opposite direction. And there is also kind of material going inside of a tank 2. So here we can see it on the diagram. So we'll be kind of uh, labeling our flows as queues, and we'll have subscripts as one, two, three, four to represent which flows which flow they represent. So before trying to figure out our differential equation for the problem, let's try to model our problem, our system. So let's say we have our queue, which is going from 1 to 2. So as we don't know the heights, the fluid, the flow is kind of connected to our heights. So here in the problem, we have that the proportionality, here we have the magnitude of the flow between tanks is proportional to the square root of the difference in fluid heights between pair of tanks. So which means our flow is proportional to the difference in heights. So we have square root of difference in heights, which is multiplied by alpha, which is going to be our proportionality constant. But as we don't know the heights of our fluids, the flow can be going either way. So what we're going to include to represent that is our sine. So it's going to change. So the magnitude of this is going to change depending on which tank has the higher fluid height. So this is the flow between tanks 1 and 2. So let's move to the tank flow 2 to 3. So it's still going to be our coefficient, right? Multiplied by the difference in heights. Oh, it's negative, sorry. To the power of half, which is the square root. And same thing with this tank. With these tanks, we don't know which way the flow is going. So we're gonna represent our flow as H2 minus H3, okay? So And we also have our flow out of the tank 3, right? So it's here, it's also going to be like the tank 3 drains to the surrounding at a height of 0 with the same proportionality constant. So it still have we still have the a alpha as a constant, and it's going to be h3 to the half, okay? And we also have like Q, like the flow entering the tank 2 from our outside surrounding. So we're going to represent that as here, as we are given here, using here we have using the simplest form of the control for the fluid level in the third tank. The flow into the second tank is set equal to the proportionality constant multiplied by the difference between the fluid level set points for the third tank. So we should have another variable, which is gonna be, so it's gonna be Qn, right? So we should have another variable which is gonna be the height set point for the tank 3. So there is a kind of specific height that we determine that is gonna be given. So we have Kcp, which is gonna be the proportionality constant for the flow coming in, multiplied by the difference in height. So we have our new variable, which is going to be height, like set point, minus height 3, okay? So this is the this is the proportionality for the flow entering the tank too. Okay, so now we have our model for our 3 tanks that are connected with each other. So now let's try to determine a differential equation to try to solve it using the Python code, which is going to be the second part of our problem. So as we have 3 tanks, we are going to have 3 individual differential equations for all of the tanks. So let's start by tank. Okay, let's start from here. Like for tank 1. So what do we know about tank 1? So we are given the cross-sectional area of each tanks, and we have to find the thing that is going to be changing by the time as the flow goes. So as the flow goes from one tank to another, the volume of a fluid inside of a tank is going to change, right? So as we are given the cross-sectional areas, the height of a fluid is going to change because it is like we know that the volume is equal to cross-sectional area multiplied by height. So we can represent the like the change in tank 1 as our cross-sectional area of tank 1 multiplied by dH1 over dt. So the change of height in tank 1 by the time. So it's only be dependent by the flow between between tanks 1 and 2, right? So we're just gonna plug, and we're just assuming it to be leaving, right? So we're gonna make it negative Q1 and 2. So if the height of the second tank is greater than the height of the first tank, here we would have the negative sign, which makes this positive. So which becomes like the flow will be going from tank 2 to tank 1. So let's describe the change of flow in tank 2. Okay, we have our cross-sectional area for tank 2, and it is going to be multiplied by the dH2 over T, which is going to be the difference, like change in height, rate of change in height 2. And here we have our Q23 leaving, or either it can be like coming to the tank, but it will be determined in our model. So we will say like it's leaving, right? And there is a Q incoming and Q12 coming. So we're gonna represent our change as Qn plus Q12 minus Q23, right? The signs might change depending on the heights. So for the tank 3, we can model it as we still have our like the cross-sectional area for the tank 3, right? And we have like the rate of change of our height in tank 3, right? And from our model, so we have a fluid coming to the tank 3 from tank 2. So we're gonna have positive Q23, and we have Q3 leaving our tank, right? So we're gonna have minus Q3. So now here we have our model for our 3-tank system with its 4 equations, and we have determined 3 differential equations which we can use to while solving the problem using the Python code. So as we are already done with our model and determined 3 differential equations, we can start writing a code to solve these 3 differential equations. So as always, let's start by importing some of the libraries that we are going to use. So we're going to use NumPy. So we're going to import it as np, and we're also going to use the plotly for plotting. So from plotly, we're going to import subplots. So from plotly subplots, we're going to import like make subplots function, and we're also like we don't want our plot to be in a white background, so what we can do is import plotly.io as pio, so then pio.template.default is gonna be equal to the plotly dark, right? And so as we're solving differential equations, what we can do is we can use the scipy integrates solve IVP function. So what this function does is, so it takes the function, and the time span and the method to determine the differential equation to solve it. Okay, we can run it. Oh, we didn't import that yet. So from scipy.integrate, right, we can import solve IVP, right? And here it says invalid syntax. So from plotly subplots import make so there's subplot, so there is a mistyping here. Still from plotly subplots import, I think there is an extra space, so that's causing an error still. So plotly io is plotly dark default. Oh, again mistyping. Oh, it was templates. I think it was templates, right? Yes. So now it's working. So if we go to our initial problem, we are given some values for our cross-sectional area and some like for the coefficients. So what we can do is we can kind of give the values for them. So we have 3 cross-sectional areas, right? So they're 0.5, 0.5, 1, and let's just make it 1 and 2. Oh, oops. So then what we also have our initial, like we have our initial heights, right? So we can make like HO1, so that it means like the initial H02, H03, so that we can assign the values for the three variables. So we have, they're going to be 0.5, 1, 1, and 2. Okay, what we also have is we also have the coefficients, right? The proportionality coefficients. So it is 0.1 for all the tanks. So what are we going to have? So alpha 1, alpha 2, and alpha 3 is going to be equal to 0.1, 0.1, and 0.1. So these are the given values that we already know. So let's now, so as we're gonna use the solve IVP function, it has to take the function inside. So let's just define a function that would calculate that would kind of return the our differential equations. So what we're gonna do it, so we can make like right hand side, and the function should take the value for temperature and y. Okay, so here we have our model, right? So for this one, all the four equations we have here as a model goes inside of our function. So we have, and so for y, all our h values are gonna go as a y. So we're gonna unpack it. So it's gonna be the y, right? Then we know that in the question we are given the set point. So the set point for the third tank. So we can have H3 SP as 4 meters. What we also have is we're given the proportionality constant. So it's going to be Kc equals 0.1. So let's now have these our like 4 equations inside of our function. So Q12 is going to be equal to NP, oh sorry, so NP dot sine, so it's going to be H1 minus H2, right, and multiplied by alpha 1 times NP. So here we forgot like multiplication here. NP absolute value of H1 minus H2, and we're gonna have to take a square root of it, 0.5, right? So, and as we have the second equation very similar to this one, we can just copy it and change the values. So we're gonna have K23, right, this time beside, so this time it's gonna be H2 minus H3. It's gonna be alpha 2, and right, and it's gonna be absolute value of H2 minus H3 taking the square root. So here we have an error because of here. So we have a mistyping here. So now it looks good. Then for our third equation, for flow out of the third tank, we're gonna have like alpha 3 times what? So it is H3 to the power of 0.5. And the last equation we have flow in, so it's gonna be the flow that is coming inside of the tank too. So it's gonna be Kc, which is the proportionality constant, times, so the change in the our set point and the third height. So it's going to be H3 SP, right? Set points minus H3. So now we have all our equations inside of our function. So this function now has to return the values for dH over dt. So it's going to return 3 values for 3 tanks. So in our equation here, so if we want only dH over dt, leave on the one side, we can divide the other side by the cross-sectional areas. So our first return value is going to be negative, it's Q12, right, divided by A1. And our second return value is going to be Qn plus Q12 minus Q23 divided by second cross-sectional area, and the last value that we're gonna get is gonna be Q23 minus Q3, right? And divided by the third cross-sectional area. So if we run this, now we have a function called right hand side that is going to return the values for the dH over dt's. So now we can use the solve IVP function, and it has to take the value, for the inside, it has to take the value so it will get a value of right hand side, right? So it will take a function, and when you go to the function here, we need a time span. So now let's just have a variable here as tn. So it's going to be the tn time. Let's make it like 500. It must be enough. So we're going to include this. So it's going to be tn, and it's going to start from 0 until the end, right? So 10, and what else? So here we have our method. So we're going to use the method of Radu, R-A-D-A-U, yes. And here we have methods. This should be fine. Oh, here I see we forgot to close the parentheses. Now if we run this, we should be 10 t end. Oh, I didn't run this. Oh, we forgot to include our y values here. So if we go to here, so we should include the y values, which are going to be our h values, right? H1, our initial h values. So we can include our initial heights. So h01, h0, h02, and h03. And comma. So now we should numpy has no attribute sign. Okay, so for the sign it was with I, so again the mistyping. sign, right? So now this should be fine. Now we get our answers here. So what we're gonna include here is we can include the dense output thing. So this is gonna return the value. So when we are solving the differential equation, we can have something like as y equals. So we can have that returned here using this. So okay, I think we did something correct. Solve. So it should get is it red? Yes, dense output should be true. Let's try to run all of this. Oh. So IVP. I think we're experiencing a problem here. Oh, that's because of using C instead of S. So now we have here the solution for our three differential equations. So if I want to get like isolate that value, I'm gonna dot sol put dot sol. So I can make this equal to sol as a variable of sol and run it. So now we have a variable sol, and we can use it for plotting. So let's just have the t for plotting purposes, right? Okay, it's gonna be, we're gonna have random numbers that are linearly spaced, so lin space, which is gonna start from 0 and add it like like ending time, which we defined earlier, and we're gonna have, let's have 500 values. And so for our heights that we're gonna plot, we're gonna have, so let's use the sol function now. So it should take the t plot as a value for time, and let's add the figure here. It's gonna be make subplots, right? We're gonna open close the brackets. So let's just, for the figure 1, we're gonna use the scatter plots, scatter x for, so our x value is gonna be equal to our t for plotting purposes, and our y is gonna be equal to our h1, right? And for our mode, we're gonna have lines. So we want our graph to be a line. So we can have a name to this. So we can have it as h1. So let's just copy it. So we should plot three lines for the 3 tanks to see the variation. So for this time, they're gonna have the same time, but so it's gonna be 2, 3. Let's name it as 2. Oh, 2, and this is 3. Right, now this should be good. Let's try to run it. Oh, here we have our graph. Okay, so this is the like the graph for our differential equations. So the model of the flow, like that, of 3 tanks that are interacting with each other. But here, where we look at it, it's a kind of straight line, right? It's not changing, which means it's a steady state. So the steady states means like all the derivatives respect to t are going to be 0 in this region. So let's just have a let's arrange for our x values so that we can have the most important part as other parts are, or we know that it's going to be a steady state. So let's just run everything. Okay, now we can see the variation between the flows of 3 tanks, and we initially we defined our set point right as a 4 meters, but here we see for our third tank it's even not going to the third, like 3 meters. So this is because of our proportionality constant. If we increase it, we can make as we increase the proportionality constant, our set, like the third tank, can go up to the 4 meter value, but it's gonna cause a very bad things with the flows of the first and the second tank. So let's have it like as 10 and run it. So you see that it's gonna oscillate, it's even gonna have like negative height, so which we don't want. So we're gonna leave it as 0.1. So using this method we cannot obtain the set value. So this problem can be solved using the other method, so which we're gonna cover in the next videos. So in this video we just use the model of 3 interacting tanks and the flow between them, and to set up a differential equation and try to solve it using the Python code. And thanks for your attention.